Hey kids, so let's give this a whirl from the beginning. We are talking about acids and bases now, and the key to acids and bases is this understanding of equilibrium. And equilibrium does not mean things are equal, it just means that they are changing at a rate that is not changing, basically. So during the school day, there are many kids in school and there are a few students that are outside of the school, and the ratio stays the same because every time someone comes into the school there's probably someone who's going to leave the school. So someone comes back from their spray tan and someone goes out to the orthodontist, but the ratio stays the same, and that's considered an equilibrium because even though there is a, it's called dynamic equilibrium, because even though things are quote unquote still in motion, the ratio is not changing. So it doesn't mean that things are equal. It just means that things are at a ratio that's not changing. If we wanted to change that, say after school, if we ring the bell, then many students will then leave after the bell rings. And then there will still be some that stay behind for practice and stuff. And then at some point after school, there will be this dynamic equilibrium reached again, where maybe someone comes back and forgets a book, but someone else leaves because their parents showed up or whatever. So it's going to stay. The ratio is going to stay the same, and that is what we consider equilibrium. Same can be true here with my cat. This is Buzz, and Buzz can either be sleeping or awake. So if I stay home on a Saturday and I want to keep track of whether he's asleep or awake, every time I see him, I might just give a hash mark to what state he's in. And after the day, I might see that he's actually sleeping a little more than he's awake. And that doesn't mean he's awake or asleep at that moment. It just means 60% of the time he's asleep and 40% of the time he's awake. And I can change this equilibrium again by doing something like introducing a bug or a bird in the house, or making the house very warm so he wants to sleep more frequently or whatever. I can change this equilibrium to favor either the sleeping cat or the awake cat. All right, so chemical equilibrium is when the amounts of reactants and products stay consistent with time, and it's because the forward reaction and the reverse reaction proceed at the same rate. So they're going to occur, like we said. It's not that they're not happening anymore, it's just that they're not happening at a changing rate. And you can affect the equilibrium of reactions by changing the conditions, adding pressure or temperature or something of that nature. All right. Chemical reactions will reach equilibrium, and that's going to help us understand the difference between a weak and strong acid. So let's first get some definitions. And I think the best definition for an acid is the Arrhenius theory, which is that acids produces H plus in water. If you have an H plus, that is an acid, and please remember that. Bases, on the other hand, will produce OH minus in water. And I will occasionally refer to H plus as a proton. That is because hydrogen is just a proton and an electron. And if we have hydrogen with a +1 charge, that means the electron's gone away, and all that's left is the proton. So H plus would just have the proton without the electron. Okay. Bases and acids react to form water. This is a very important part of what we're going to do with titrations, is we're going to take acid and base and combine them until they form neutral water. And that's always fun to do. Anything else, so the Na and the Cl here, so the Na and the Cl, you may be wondering, well, what's going on with those? Why don't you talk about those? Why do you only talk about the H plus and the OH minus? Because those are spectator ions. They don't do much. They just basically watch what's happening with the H plus and OH minus. All right, so acids typically have the formula where with a leading H, Ha, where the H is acting basically like a metal in ionic compounds. It's the first thing listed and it has a positive charge. The anion's charge will dictate how many H's you need. So hydrochloric acid, where you have Cl minus 1, needs 1 H. Sulfate, SO4 minus 2, would need 2 H's. Phosphate, which is minus 3 charge, would need 3 H's to be neutral. So these are just some examples of some acids. These are strong acids. Weak acids are acids that you can drink and whatnot. We're talking about vinegar, vitamin C, formic acid, citric acid. These are acids that are familiar to you, maybe not formic, but the other ones. And the fact that you can ingest them means obviously they're not doing a lot of damage to you. So therefore, they are what we call weak acids. And we'll discuss what the difference is between those. All right, bases typically have the formula of a metal plus an OH. And again, the charge of the metal in this case will determine how many OHs there are. So group 1 metals like sodium, lithium, potassium only need one OH because they always have a +1 charge to go with that -1 charge. Calcium, magnesium, barium have a +2 charge, so they need two OHs, each with a -1 to counterbalance that. All right, now weak bases tend to be amines. Amines have the formula with an N in it and then some H or something 3 times. So ammonia and H3, or triethylamine with an N with C2H3, C2H5 3 times. The amine has this lone pair, and that's what makes it a weak base. All right. Ammonium hydroxide is another example there. So let's identify these as acids or base based on what we're looking at here. So here's an OH. There's no leading acid, so that's a base. Here's leading H, so that's an acid. Here is N at the front, so that's a base. Here's an N at the front, so that's a base. Here is calcium with 2 hydroxides in there, so that's a base. Lithium with a hydroxide in there, that's a base. Here's a leading H, so that's an acid. Here's a leading H, so that's an acid. Oops. N at front, and that's a weak base. And then, actually, that's probably a stronger base. Leading H, so that's an acid. That's a weak acid. All right. So now that we did that, what makes a weak versus a strong acid is a strong acid is 1 OA. That means you have like 95% things happening on this side and about 5% of things or less hanging out as a complete molecule where the H is stuck to the Cl. So if the H separates itself and starts floating around water, that's considered a strong acid. If it doesn't, if it stays like 50-50 here, so 50% is here and 50% is here, then that's considered a weak acid where that H is connected to the acetate here more often or as often as it is free to do damage. So that is the difference between a weak and strong acid. And we did a little FET with that. And the best thing I could think of as far as an analogy is Stitch. If you're familiar with this movie, Lilo and Stitch, which I showed you in class, Stitch causes trouble. When he's alone, bad things happen. So that's sort of like this H alone. When H is by itself, it's causing trouble and doing the things acids do, like destruction. When Stitch is with Lilo, that's like that HA. So this is like that HA, like HC2H3O2, where because they're together and he's kind of stuck to her, he's not doing any damage. So here, if you have an acid that stays with its acetate anion, or if you have an acid that stays with its citrate anion or whatever, it's going to be a weak acid because this anion is going to help keep it calm and not go do all the damage. All right, now another definition for acids is Bronsted Lowry. They kind of just piled on to what Arrhenius said, and they said instead of saying H plus in water, well, you know, if H plus is really a proton, and a proton is this very small positively charged particle, then chances are it's not going to just sit and do nothing. It's going to go glom on somewhere. And so what it does is, if there's water there, this lone pair, which has a negative charge, will attract that proton, and the proton will just sort of stick to the water and make H3O plus. So instead of saying acids have H plus, Bronsted Lowry said acids have H3O plus, and they defined bases as a proton acceptor. So it wasn't just limited to OH minus. Now anything that had a lone pair that could accept that H plus hanging around is considered a base. And that allows for a better understanding of those weak bases that we were talking about, the amines and such. All right, so then the last thing we talked about here was the constant, the rate constant. So it turns out if you have any constant, in this case, how many M&Ms fit into Easter egg, it turns out there are 48 M&Ms that'll fit in there. So if I wanted to put 48 M&Ms and I wanted them to be white and yellow, I could choose to have all my M&Ms white, but that means I can't have a yellow. Every time I want to add some yellow, I have to take some out of the white because only 48 will fit perfectly into that egg. So as I increase this yellow number, this is decreasing. My white is decreasing to counteract. And if we were to graph that, it would be an X like this, where you see as the white ones go down, the yellow ones are going up. So that's an inverse relationship. And the reason that's relevant to what we're doing is it turns out there is an equilibrium constant. Every time water has H plus and OH minus in it, the concentrations of those when multiplied equal 10 to the minus 14. And that constant limits how much you can have of each one. So if, for example, let's discard everything I just did, and hopefully I had it up and running, but I don't. So we're just going to quickly, and hope my internet's working all right. Fat acids. All right. Let's see if that one works. That's not what I wanted. pH. All right, let's go with that one. Okay, so if we have, if we're going to add OH, then the H plus has to go down because the two have to equal, the concentration of this times concentration of this have to equal 10 to the minus 14. So as one goes up, the other goes down. As the other one goes up, the other one has to go down. So as you can see here, there's this inverse relationship between the H plus and the OH minus, and that's how come to have a basic solution, you have to have very little H plus, and to have an acidic solution, you have to have very little OH minus and lots of H plus, as you can see here by the colors in the solution. All right, I don't know how much sense that made, but we're going to keep going anyway. So we're going to assume you know how to do math with tens, but if you graph this out now, as this H plus decreases here, your OH minus increases. Now the problem is, because this is a tenfold difference every time, this is 10 times 10 to the minus 1 is 10 times 10 to the minus 2. 10 to the minus 2 is 10 times 10 to the minus 3. Because of that huge jump every time, there is a huge drop off, and you can't even see what's going on right here in the graph, because we would have to blow that up to see the difference in each case. So because of that, this graph looks sort of like a U, and it's kind of boring. What we do then is we introduce log, and what log does is it accounts for the exponential function of 10. So we should embrace logs as we're doing this unit. The log function just means 10 to the power of minus 5 means what power do you have to raise 10 to equal this number, 10 to the minus 5. And it turns out that's minus 5. What power do you have to raise 10 to equal 10 to the 43rd? That's 43rd. So basically 10 to the power of whatever, if you're trying to find the log of that, it equals the whatever it is you're holding the exponent to, whatever exponent of 10 you're dealing with. So pH is defined as the log of H plus, but because that would always be negative, because all your concentrations will have a negative exponent, we wanted things to be positive, so we defined it actually as the negative log of the pH, of the concentration of H plus. So whatever the concentration of H plus is, we take the log of that, so it's whatever the exponent is. Basically, it's a little more complicated than that when you hit the button on your calculator, but basically that's what's going on. And then we're going to make that positive, so therefore we would need to make it the negative log, so that's always positive. So let's look here. 0.1 is 10 to the minus 1, the negative log of H plus, so the log of 10 to the minus 1 is just what the power is here, minus 1. And if we want to make that negative, the negative of negative 1 would be positive 1, so the pH is 1. 10 to the minus 3, the log of that is minus 3. Negative minus 3 is positive 3, so therefore the pH is 3. This would be 5 and 5, 7, 7, 10, 10. So as you can see, though, these numbers, even though they have negative exponents, are not negative. This is not a negative number. This is a very fractional number. This is a very small fractional number. These aren't negative numbers. The exponent is negative, but it's just accounting for how many times you're moving that decimal point with the zeros over there. All right, so what does log do? Log turns this graph into this graph, a nice pretty graph like we had before, linear x, where as the pH is getting larger, the POH has to be getting smaller to account for that. And you can see here in each case, they equal 14. Every time you can add these up and equal 14. All right, so the overall point of this is that a pH of 1 to 6 means H plus is greater than OH minus, and therefore the solution is acidic. So we're talking about, right, pHs in the low region have more H plus. And if we have pH of 8 to 14, that means your OH is dominating. OH is dominating on this end of things because it is high, and therefore the H plus has to be low. So that means it's a basic solution. And if they're equal, then that's 7, which is neutral. All right, that's all I'm going to say with that. Hopefully that works for you, and best of luck.